Okay, so I guess we can start with today's webinar. First of all, I want to welcome everyone and thanks for joining us today. Just a quick note before we start, this webinar is being recorded and the recording may be made available later as part of the HYIELD Project's communication and dissemination activities. Like I said, this session is part of the HYIELD Project, one of our outreach communication and dissemination actions. The project is co-founded by the Horizon Europe and the Clean Hydrogen Partnership. Today's session is titled Gasification of Different Biomasses in a Bubbling Fluidized Bait Reactor, Influence of Process Variables. Can everybody hear me?
Yes, Laia, we can hear you.
Okay. All right. So I don't know why Alejandro can't then. All right. Sorry. Thank you. All right. So as I was saying, the session today, yeah, I think it's Alejandro's problem. So today's session is titled, like I was saying, Gasification of Different Biomasses in a Bubbling Fluidized Base Reactor, Influence of Process Variables on Gas Yield and Composition. And we're very happy to have Andrés Viedma from McTel and Ramón Murillo from CSIC with us. If you can please turn your cameras on, Ramona and Andrés.
Yes, hello, everybody.
Hi, hello. Okay, so I would like to remind everyone that we'll have a Q&A at the end of the session. So please drop your questions in the Q&A section, which is at the top, slightly on the left of the bar. And the more questions, the better. So please don't be shy. And we'll try to get through as many as we can. We are now halfway through HYIELD, and this webinar is fully focused on what we call Work Package 1. And this work package covers experimental work that sets a technical basis for everything that comes later in the project. Today, we'll look at gasification tests carried out with different biomass feedstocks in a bubbling fluidized base reactor. And we'll discuss how key operating parameters like temperature, steam to carbon, and equivalence ratios affect gas yield, syngas composition, and carbon conversion. These results are crucial for understanding feedstock flexibility and for supporting the design of the downstream HYIELD process. And now a quick intro for our speakers. We have, like I said, Andrés Viedma. He is a mechanical engineer working in the R&D department at McTel, where he's involved in developing innovative and sustainable energy technologies. Andrés will kick off things by introducing the HYIELD project and giving some context. And then we'll hear from Ramón Murillo, research professor at the Institute of Carboquímica, or CSIC. Ramón has more than 25 years of experience in biomass and waste thermochemical conversion, especially gasification and pyrolysis. And he'll walk us through the main experimental results from said work package. And with that, I'll hand it over to Andrés to get us started. So Andrés, please, if you can share your screen.
Okay. So, well, thank you, Laia, for the introduction. And hello, everybody. Thank you for being here today. Like Laia said, I'm going to present HYIELD to all of you. I'm going to talk a little bit more about the goal and why HYIELD was born at first. And then Ramón is going to talk about the technology, who is more expert than me on this field. But I'm going to try to explain it so everybody understands where we are now and why we created this project. So first of all, HYIELD, it's a multi-stage steam gasification and syngas purification system. Our goal is to convert biomass into hydrogen, and to do so we developed this technology with the gasification in order to produce a really high purity hydrogen and to get the best conversion that we can with our biomass. So first of all, we want to make this clear, HYIELD comes from hydrogen, like I just said, and as it is to increase hydrogen use from waste conversion, we want to make it clear how it has to be said, because some people say high yield or higher or different ways, so it's HYIELD. Well, just to start, HYIELD is under the Horizon Call from the European Union. It has a total budget of 15 million and a total grant of 10 million euros. It started on January 2024 and it goes all the way until December 2027. So it's a more or less 3 years period for this project. And like I said before, the main goal is to develop a multi-stage steam gasification and gas separation process for biomass conversion. And this solution is going to be demonstrated at a 3 megawatt plant that is located in a cement plant in eastern Spain. I'm going to later on talk about the location of this plant and how this is going to be implemented. So we have our final user, which is going to help us to demonstrate and validate our technology. The consortium, it's formed by many companies from all around the world. We have some research institutions and technology centers as EURECAT, CSIC, which we have Ramón here, Sintef, some technology developers as MacTel, that's where I'm working at. And like I didn't say at the beginning, but we work on the development of this technology as well. Waste to energy, H2Side or Mincatec. We have other companies as Cemex, Enegas, Lafarga, ArcelorMittal or Synelion for industrial corporations. And then we have Veolia and Setaqua, waste managers as feedstock suppliers, and engineering and strategy consultancies as Aristein or Invenian. So as you can see, the consortium is really big and we have a lot of companies involved. We are working together to make this project the best we can. Our main vision or goal, why all this started, is, like I said before, to give all this waste disposal a new life and a better life after it is produced. Especially on some low population density areas, as it could be islands, for example, where the infrastructure is more limited, and the common methods for the treatment of this waste is landfilling or incineration, which is causing a lot of CO2 production and is not helping our planet at all. So not only this, but also that this is expected to keep growing. The tendency is going up, and especially for the next coming years with industrialization, a lot of waste is expected to be created, around 3.4 billion tons by 2050. So if we are able to really explode this waste and convert it into energy, we can cover a lot of needs, necessity of a lot of communities all around the world. And then the challenge for the treatment of this waste is that this is not, this is, well, heterogeneity, and the composition is not the same, you know, so we need to analyze different kind of biomass and how you treat it, and it's not the same technology that can be applied to all of them. We can also decarbonize some sectors that are difficult, and it's a challenge nowadays, as it is shipping, aviation, and the cement industry. That is our main focus for our demonstration plan. And our solution is a gasification of waste and organic material to extract this hydrogen that I'm talking about through the gasification process. And the main motivation is to develop a new low-cost pathway for waste management and clean hydrogen production. The plant is going to be located in Catalonia, instead of Spain. Here you can see this is a picture of Cemex plant where they produce cement, and we are going to deploy our waste plant on this site. As we can see in the picture, we have already planned where it is going to be located, how it is going to be accessed, and all the connections to the cement plant for them being able to utilize this energy that we're going to be producing with our hydrogen in the cement production. The plant already has some key aspects that is going to help for the best development of our project, as it, for example, has some environmental authorizations, like which includes the use of waste. And then it also has various sources of waste heat. It also has industrial cleans with hydrogen injection and the possibility of reintegrating hashes in raw materials. The process like the whole idea of HYIELD is to use this waste that is produced. CSIC and Veolia are the main partners in charge of these parts of the process. They are the ones in charge of the management and supply of this waste. Then they take it to our main plant, where the whole technology is deployed, and with the gasification, we're able to convert this waste into gas. Then the purification of the gas through a membrane reactor, and after that, we are able to storage our hydrogen for then being able to use it in the cement industry. We have divided this process in 4 different stages. Stage 1 will be a stage of planning. This is process validation, specification, and basic engineering for the demonstration plan, and it is around tier 5 and 6. Then we go on to stage 2, which is the development of the technology, where we are going to develop a digital twin, site preparation of the plant in the picture that we saw before, the waste feedstock management, and the detailed engineering and manufacturing installation. After that, we go on to stage 3, which is the demonstration phase, with validation and extended testing periods on the final user that, as I said before, it's Cemex for this case. And finally, stage number 4 is a scale up, and it's an analysis of how we can scale up this technology and use for different user cases, and not only in the cement industry, but also in aviation or other industries, and how also this is going to impact on the techno-economical analysis. Right now, we have gone through stage number 1 already, and we are on stage number 2, working on our digital twin, site preparation, waste feedstock management. Basically, that's where we are right now. So we still have some work to do ahead of us, but it's going pretty well, and we are working really hard for it. I hope we can get to stage number 4 soon. And well, this is a small diagram of the project. It starts, like I said, end of 2023, beginning 2024 at tier 4. It is supposed to go all the way to tier 7 around 2030. And for this, it's gonna go through lab validation process. That's, I would say, where we are now, and then the process design optimization for all the plants, and until we are able to build a prototype and to scale it up for the use in different industries. Our markets where we want to operate and we were to take this technology to, it's the copper sector, cement sector, steel sector, but not only this, of course, also in the aviation, industrialization of all different type of technologies. And I mean, the overall goal is to decarbonize the power plants in the European Union. And it's our goal for the European Commission, and that's why we work so hard for it. So thank you everybody for your time. Now I give the word to Ramón, and he will explain the technology a little bit more.
Okay, thank you, Andres. Good morning, everyone. I'm going to share my screen right now. Okay, so yeah, as I was saying, good morning, everyone, and thank you for attending this webinar. My name is Ramón Murillo from the Environmental Research Group at the Instituto de Carboquímica that belongs to the Spanish CSIC, that it is the largest research establishment here in Spain. Well, today I will present an overview of gasification technology applied to different biomass feedstocks with a special attention to bubbling fluidized bed reactors and to the influence of the different operating variables on gas yield and gas composition. This slide summarizes why biomass and waste gasification is relevant today. Gasification, probably you know that it is a thermochemical route that converts solids or liquid carbonaceous materials into a gaseous product, generally called syngas. This syngas contains mainly hydrogen, carbon monoxide, carbon dioxide, methane, and light hydrocarbons, and it can be used as a platform gas for different applications. There are two main types of feedstock of interest. The first one is biomass, which contains biogenic carbon and includes residues from forestry, agriculture, and agroindustry. These materials are renewable and can contribute to reducing the use of fossil resources. The second group is waste, especially non-recyclable fractions like RDF, plastics, and mixed residues. These materials are more complex and usually require robust pretreatment, but gasification offers a possible route to recover their carbon and energy content. The strategic value of gasification is that it can produce several products from the same type of platform gas. Depending on the downstream process, syngas can be used for heat and power generation, hydrogen production, synthetic natural gas, methanol, or even Fischer-Tropsch liquids. Another important point is carbon circularity. Instead of simply burning waste carbon or disposing of it, gasification can convert it into useful gases and chemical intermediates. However, this also requires proper integration with gas cleaning because the final syngas must meet the specifications of the intended application that sometimes I have to say that are really very hard. This slide puts gasification into historical content. Gasification is no new. It has more than 2 centuries of development. What has changed over time is not the basic thermochemical principle, but the feedstock and the reactor designs and the final objectives of the process. In the 19th century, gasification was mainly associated with coal conversion in fixed bed reactors. The resulting town gas widely used for lighting, cooking, and heating in cities before the large-scale availability of natural gas and electricity. During the first half of the 20th century, gasification became increasingly important for industrial gas production and power applications. Producer gas was used in industry, and syngas chemistry also developed strongly during this period, including the water-gas ship reaction and other routes for gas upgrading. In the 1940s and 1950s, gasification played a strategic role in the production of synthetic fuels, especially through Fischer-Tropsch chemistry. Syngas could be converted into liquid fuels and chemicals, which was particularly important in periods of limited access to petroleum, like in the Second World War. Later, between the 70s and the 90s, the oil crisis renewed the interest in gasification. During this period, large pilot plants, demonstration units, and IGCC concepts were developed, mainly focused on coal gasification and power generation. During this century, the focus progressively shifted towards biomass and waste gasification. The objective was no longer only to produce a fuel gas, but also to valorize renewable and residual feedstocks, produce heat and power, generate synthetic fuels, and develop routes towards circular carbon. Today, gasification is increasingly connected with decarbonization strategies. For example, advanced concepts such as indirect gasification, short-term enhanced gasification, and chemical looping gasification are being developed to produce higher quality syngas, hydrogen gases, and concentrated CO2 streams. This slide focuses on the basic fundamentals of gasification. Gasification is a thermochemical conversion process in which a solid or liquid fuel is transformed into a combustible gas or syngas using a limited amount of oxidant or steam. The key point is that the process does not operate under full combustion conditions, and only part of the fuel is oxidized, and the heat released by these partial oxidation reactions drives the rest of the conversion process. Inside the reactor, several stages take place, often simultaneously. First, the feedstock is dried and moisture is evaporated. Then the volatilization or pyrolysis takes place, releasing volatile compounds and producing char. After that, partial oxidation reactions generate heat, while the cracking, reforming, and char gasification progressively convert the solid and volatile products into permanent gases. The final raw gas contains mainly hydrogen, carbon monoxide, carbon dioxide, and methane, together with light hydrocarbons, tar vapors, and particles. Therefore, gasification should not be seen as a single reaction, but a sequence of coupled thermal, heterogeneous, and gas phase processes. In this slide, this slide summarizes the main reactions involved in gasification. The first group is oxidation reactions. Partial oxidation of carbon produces carbon monoxide and releases heat, while complete combustion produces carbon dioxide and releases even more heat than the partial oxidation. These reactions are essential because they supply the energy required for the endothermic steps of the process. Then we have the boudoir reaction, where carbon reacts with carbon dioxide to form carbon monoxide. This reaction is endothermic, becomes more important at high temperature, and contributes to increasing the CO content of the syngas. Another key reaction is steam gasification, where carbon reacts with steam to produce carbon monoxide and hydrogen. This is one of the main routes for increasing hydrogen production when steam is used as gasifying agent. The water gas reaction converts carbon monoxide and steam into carbon dioxide and hydrogen. It strongly affects the hydrogen-CO ratio and is especially relevant for hydrogen production or synthesis applications. Finally, methane can be formed or consumed through methanation and reforming reactions, depending mainly on temperature. The key point is that all these reactions compete with each other and are affected by temperature, pressure, steam content, oxygen supply, residence time, and catalytic effects. Also, char gasification is usually slower than the volatilization and gas phase reactions, so it can limit the overall solid conversion. This slide introduces the main gasification routes from the point of view of oxidant supply, heat supply, and product gas quality. The simplest option is air gasification. Air is, of course, really very cheap and readily available, and part of the fuel is oxidized inside the reactor, making the process partially or fully autothermal. However, the main drawback of nitrogen dilution is nitrogen dilution, since air contains a large amount of nitrogen. In this way, the resulting product gas has a relatively low heating value and is mainly suitable for direct heat or combined heat and power applications. A second option is oxygen gasification or oxygen steam gasification. By replacing air with oxygen, nitrogen dilution is largely avoided. As a result, the concentrations of carbon monoxide and hydrogen increase a lot, and the gas becomes more attractive for upgrading or synthesis applications. The disadvantage is that oxygen has to be supplied usually through an air separation unit, which increases cost and, of course, complexity of the final plant. Steam can also be introduced as a gasifier aid. Steam promotes char gasification, reforming reactions, and the Worcester-Gassiff reaction, favoring hydrogen production and increasing the hydrogen to CO ratio. However, steam gasification is highly endothermic, so the reactor requires an efficient heat supply. This is where advanced gasification concepts become important. Instead of simply feeding air, oxygen, or steam into a single reactor, modern processes try to separate or control the key functions: heat generation, syngas production, CO2 capture, and oxygen transfer. In the next 3 slides, we will go through 3 different gasification concepts. Here we can see the concept of indirect gasification using a circulating heat carrier, which is the same principle applied in the industrial Gussing plant in Austria. In this configuration, the process is divided into 2 interconnected reactors. On the left, we have the gasifier, where biomass reacts with steam under oxygen-free conditions to produce a nitrogen-free syngas. Because no air is introduced into the gasifier itself, the product gas is not diluted with nitrogen, which significantly increases its heating value and hydrogen concentration. The remaining char and bed material are then transferred to the combustor shown on the right. In this second reactor, the char is burned with air, generating the heat required for the process. The hot solids, typically olivine or another bed material, circulate back to the gasifier and provide the thermal energy needed for steam gasification. A typical dry gas composition for this type of process is around 40% hydrogen, 25% carbon monoxide, 20% carbon dioxide, and about 10% of methane, with only a small amount of nitrogen. This slide shows the concept of sorption-enhanced gasification, or SEG, using the calcium looping system. The process is quite similar to the indirect gasification. Well, in fact, it's a kind of indirect gasification, but now a CO2 solvent is typically calcium oxide, is introduced directly into the gasifier together with the biomass and steam. Inside the reactor, calcium oxide captures carbon dioxide in situ through the carbonation reaction, forming calcium carbonate. By continuously removing CO2 from the gas phase, the chemical equilibria are shifted towards hydrogen production, especially through the water-Gassiff reaction. As a result, the syngas becomes highly enriched in hydrogen. For example, typical dry gas composition can reach around 70% hydrogen, while CO and CO2 concentrations are significantly reduced. The carbonated sorbent, together with the char and bed material, is then transferred to the calciner or regenerator. In this reactor, calcium carbonate is calcined back to calcium oxide, releasing a concentrated CO2 stream and regenerating the sorbent for recirculation to the gasifier. Finally, this slide presents the concept of chemical looping gasification, or CLG, using a solid oxygen carrier. In this process, oxygen is not introduced directly into the gasifier as air. Instead, a metal oxide transfers lattice oxygen between 2 interconnected reactors. On the left, biomass reacts with the steam and the reduced oxygen carrier in the fuel reactor. The oxygen supplied by the solid promotes partial oxidation and gasification reactions, producing a syngas rich in hydrogen and carbon monoxide. Since air does not enter this reactor directly, nitrogen dilution is largely avoided. The reduced carrier is then circulated to the air reactor, where it is reoxidized with air and heated before returning to the fuel reactor. In this way, the solid continuously transports oxygen and heat between both reactors. Typical CLG gas compositions contain around 30% hydrogen, 30% carbon monoxide, and about 20% carbon dioxide, with low nitrogen content. This slide compares typical dry syngas compositions obtained with different gasification technologies. Starting with conventional air gasification, we can see that the product gas contains a very large amount of nitrogen, typically close to 50%. This happens because air is directly introduced into the reactor, and nitrogen acts mainly as a diluent. As a consequence, the syngas has a relatively low heating value and is usually more suitable for direct combustion or combined heat and power applications, rather than synthesis processes. When oxygen is used instead of air, nitrogen dilution is almost eliminated. This increases the concentration of carbon monoxide and hydrogen, producing a medium heating value syngas that is more attractive for upgrading and chemical synthesis. If steam is added together with oxygen, the hydrogen concentration increases even further. Steam promotes reforming reactions and the water-gas shift reaction, shifting the gas composition towards higher hydrogen to CO ratios. Indirect gasification also produces a nitrogen-free or nearly nitrogen-free gas because air is separated from the gasification reactor. In this case, heat is supplied indirectly through circulating hot solids, allowing the production of a higher quality syngas with relatively high methane and hydrogen contents. The most hydrogen-rich gas is obtained with the sorting-enhanced gasification process. Here, as we have seen, CO2 is captured in situ by calcium oxide in the gasifier, which shifts the equilibria externally towards hydrogen production. Finally, chemical looping gasification uses a solid oxygen carrier instead of direct air injection, and this allows partial oxidation and heat transfer without mixing air and syngas. This slide introduces the main reactor configurations used in gasification. On the left, we have fixed or moving bed gasifiers. These are relatively simple and robust systems where the solid fuel forms like a packet bed and moves slowly towards, through different reaction zones. The typical reaction zones are drying, pyrolysis, oxidation, and reduction zone. The gas can flow upward, downward, or even across the bed, depending on the design. These reactors are attractive at a small or medium scale, but they usually show a strong temperature and composition gradients. On the right, we have the typical bubbling fluidized bed gasifier. Here, the gas velocity is high enough to suspend the bed material, creating intense gas-solid mixing. This improves heat transfer, gives a more uniform temperature inside the reactor, and makes the system more flexible for heterogeneous biomass and waste feedstocks. The second slide shows more advanced gasifier configurations. On the left, circulating fluidized bed gasifiers that operate at higher gas velocity than bubbling fluidized beds. A significant fraction of the solids is entrained out of the reactor and then recovered in a cyclone and returned to the gasifier. This solid circulation improves heat transfer, residence time control, and carbon conversion, making circulating beds suitable for larger throughputs. On the right, entrained flow gasifiers operate in a very different, they operate in a really very different regime compared to the fluidized bed reactors. The feedstock must be finely ground or introduced as a slurry, and it reacts with oxygen and steam at very high temperature. In this way, residence times are very, very short, but carbon conversion is high and tar formation is usually very low. This makes entrained flow gasification attractive when a clean synthesis gas is required. However, this comes at the cost of higher complexity because we have to invest a lot in feed preparation, oxygen supply, high temperature materials, and as and slag handling that are, of course, critical issues. This slide highlights two aspects that are often decisive in real gasification operations: tar formation and char conversion. Tar is formed mainly during the volatilization and pyrolysis stages. At first, primary tar contains relatively reactive compounds, but these compounds can evolve into more stable secondary and tertiary aromatic species. If temperature, steam availability, residence time, or catalytic activity are sufficient, part of this tar can be cracked or reformed, producing additional permanent gases such as hydrogen and carbon monoxide. If tar is not converted, it can condense downstream and cause fouling, plugging, and even catalyst deactivation. This is why tar is usually one of the main constraints for gas cleaning and process integrations. Char follows a different pathway because after pyrolysis, part of the carbon remains as a solid char inventory. This char reacts more slowly with steam and carbon dioxide through heterogeneous gasification reactions. Therefore, char conversion depends strongly on particle size, feedstock properties, as composition, wet material, temperature, and solids residence time. Incomplete char conversion reduces carbon conversion and increases solid residue. But in fluidized feds, for example, the char inventory can also contribute to the heat balance and help stabilize the process. At this point, it is important to remember that roasting gas normally contains particles, alkali compounds, sulfur, chlorine, and nitrogen-containing species, and of course, tars. These impurities are harmful for downstream processes because they can foul equipment, condense in lines, corrode materials, poison catalysts, and prevent synthesis or hydrogen purification. For particulate removal, the first barriers are usually cyclones and hot gas filters, such as ceramic or candle filters. For acid and trace contaminants, different options are available, including wet scrubbers, sorbent beds, and activated carbon polishing. Tar can be handled in two main ways. One option is to cool the gas and remove tar by condensation or scrubbing, for example, using water, venturi, or oil scrubbers. The second option is to keep the gas hot and convert tar before cooling. This is especially attractive when gas efficiency must be preserved. In this case, catalytic beds based on dolomite, olivine, or nickel catalysts can promote cracking and reforming, and more intensive options such as thermal cracking or thermal plasma can also be used for very refractory tars. After cleaning and conditioning, syngas can be considered as a platform intermediate for several downstream products. If the target is hydrogen, the gas is usually sifted with steam to maximize hydrogen production, followed by carbon dioxide removal and a final purification step such as pressure swing adsorption or membranes. This is the case of HYIELD project, of course. If the target is methanol synthesis, the hydrogen to CO ratio must first be adjusted, and the clean gas is then converted catalytically into methanol. If the goal is synthetic natural gas, methanation is used to convert carbon oxides and hydrogen into methane. For liquid fuels, syngas can be processed through Fischer-Tropsch synthesis to obtain hydrocarbons that are later upgraded into diesel, naphtha, or sustainable aviation fuels. More generally, syngas can also be used for heat and power generation or as an intermediate for ammonia and other chemicals. Before moving into the gasification experimental results, let me briefly introduce the HYIELD project, which provides the framework for the experimental work presented in the next part of the webinar. HYIELD is a European project, as we have seen before, focused on producing high-purity hydrogen from biogenic waste streams. The general route is based on deoxy steam gasification, followed by syngas cleaning, conditioning, and hydrogen separation. In other words, the waste is first converted into raw syngas, and this syngas is then upgraded to obtain hydrogen of very high purity. From the gasification point of view, the key issue is that the raw syngas must be suitable for the downstream purification units. This means that not only the main gas composition is important, but also the presence of tar, particles, sulfur compounds, chlorine species, and other contaminants. Within HYIELD, our group has worked on the experimental evaluation of gasification performance in a bubbling fluidized bed reactor. We tested different biogenic feedstocks and different operating conditions, and we analyzed gas yield, gas composition, fixed carbon conversion, tar formation, and sulfur release. The objective was to generate experimental data that can support the design and optimization of the complete waste-to-hydrogen process. So after this general context, the following slides will present the experimental matrix, the feedstock characterization, the pilot gasification unit, and finally, the main results obtained in the project. The following slides present a selection of experiments carried out with the HYIELD project. These experiments are discussed to illustrate the effect of gasification temperature, the effect of the steam to carbon ratio, and the effect of the feedstock. For this purpose, 4 representative biomasses have been selected: structural, olive stones, grape seeds, and sewage sludge. The selected feedstock present very different properties, and this is important because feedstock composition has a direct impact on gasification behavior. First, looking at the approximate analysis, olive stone and grape seeds show relatively high volatile matter and low ash content, which is typical of lignocellulosic biomasses. In contrast, sewage sludge has a much higher ash content and a much lower fixed carbon content. This means that its gasification behavior is expected to be more dominated by the volatilization and less by char gasification reactions. The structural material shows an intermediate behavior. It contains a significant amount of ash and fixed carbon, and it was pelletized before being used in the gasification experiments. This pelletization step was necessary to improve feeding stability and make the material suitable for continuous operation in the pilot plant. The ultimate analysis also shows clear differences between the feedstock sewage sludge. The feedstock sewage sludge contains higher nitrogen and sulfur contents than the lignocellulosic biomasses, which is relevant because it can lead to higher formation of nitrogen and sulfur containing compounds in the product gas. This is especially important when the syngas is intended for downstream hydrogen purification. Finally, the heating values are also different. Grape seeds and olive stone show the highest heating values, while sewage sludge has the lowest value, mainly due to the high ash content. Okay, this slide shows the bubbling fluidized bed gasification pilot plant used at CSIC for the experimental work carried out within the HYIELD project. The core of the system is the fluidized bed gasifier, where the biomass is converted into raw syngas under controlled operating conditions. The reactor is fed with biomass through a water-cooled screw feeder, while the bed material is introduced through a separate insulated screw feeder. Steam, air, oxygen, and nitrogen can be supplied to the system, which gives flexibility to operate under different gasification atmospheres and equivalence ratios. Inside the reactor, the bed is fluidized, and the intense gas-solid contact provides good mixing and heat transfer, which are key advantages of bubbling fluidized bed reactors when working with heterogeneous biomass and waste feedstocks. Downstream of the reactor, the raw gas first passes through cyclones, where most of the entrained particles and fines are removed. After that, the gas treatment line includes specific reactors for chlorine removal, sulfur removal, tar reforming, and water gas shield. Finally, the gas is cooled in a condenser. The flow rate is measured, and the gas composition is monitored online before being sent to the flare. So this pilot plant allows us not only to study the gasification step itself, but also to evaluate the quality of the raw syngas and its suitability for downstream cleaning, conditioning, and hydrogen production. A product gas is sampled downstream of the gasifier using a standardized coal tar sampling tray. The gas passes through first through a particle filter and then through a series of impingers bottles filled with isopropanol. The impingers are operated at ambient temperature and at -20 degrees C in order to condense tar and water. A pump is used to control the gas flow rate, which is continuously monitored by a gas counter. Typical sampling times range between 15 to 30 minutes. After each experiment, all condensed liquids collected in the impingers are combined into a single amber bottle. The complete sampling system is then rinsed with isopropanol to ensure full recovery of condensable compounds. The total collected volume is recorded and used for subsequent tar quantification. That is done by GCMS for the collectible tar, for the collectible tar, but for the case of the gravimetric tar, an aliput of the collected liquid sample is concentrated using a rotary evaporator. The remaining residue is then dried for 24 hours using silica gel in a desiccator, and finally the mass of gravimetric tar is determined using an analytical balance. Okay, now we are moving to the, finally we are moving to show the results that we obtained during this long experimental campaign. In this first slide, we can see the effect of temperature on biomass gasification using structural as feedstock. Experiments were carried out at 650, 750, and 850 degrees, keeping the steam to carbon ratio constant. In this first figure, we can see the hydrogen concentration, and we can see an increase in the hydrogen concentration when the temperature is raised from 650 to 750. However, at higher temperature, a slight decrease in the hydrogen molar fraction is detected. This behavior is mainly associated with the reverse water gases reaction, which becomes more favorable at high temperatures and leads to hydrogen consumption. At the same time, light hydrocarbons, such as methane and C2 to C4, compounds clearly decrease as temperature increases. This trend reflects the enhancement of thermal cracking and steam reforming reactions, which promote the decomposition of hydrocarbons into smaller gaseous species. When temperature is increased, a significant rise in the total amount of gas produced is also observed. This is directly related to the higher fixed carbon conversion achieved at elevated temperatures, indicating a more complete conversion of the solid phase. As a result, although the hydrogen molar fraction is slightly lower at 850 degrees, the strong increase in total gas yield has a major impact on the individual gas production. Consequently, the highest absolute hydrogen production is achieved at the highest temperature studied. Overall, increasing temperature clearly improves gasification performance, enhancing gas quality and conversion efficiency. This slide shows the effect of temperature on tar formation and composition. Starting with collectible tar, the highest tar production is observed at 650. At this temperature, the tar profile is dominated by phenolic compounds and BTEX, which are typically products of primary devolatilization reactions. When the temperature is increased to 750, a clear reduction in total tar content is observed. Phenolic compounds significantly decrease, while BTEX compounds are still present, but at lower concentrations. At 850, the total tar content reaches its minimum value. Heavy tar compounds, especially PAH, almost completely disappear. This behavior confirms the strong effect of temperature on tar cracking and reforming reactions. In this slide, we can see the effect of steam-to-carbon ratio on the process performance. Although increasing the steam-carbon ratio promotes reforming reactions and reduces light hydrocarbons, at 650, hydrogen does not increase in molar fraction because the water-gas reaction is kinetically limited. The additional steam mainly generates CO through gas-solid reactions, without this CO being efficiently converted into hydrogen. As a consequence, carbon monoxide accumulates and increases the concentration. CO2 remains more or less stable or even decreases a little bit, and hydrogen is diluted in the total gas mixture. Only when steam-carbon ratio exceeds a threshold value around 2, methane reforming and char gasification become activated, allowing a real increase both in individual hydrogen production and its molar fraction. These results show the effect of the steam-to-carbon ratio on tar formation and composition. At a steam-carbon ratio of 1, the highest tar production is observed. The tar profile is dominated by phenolic compounds and BTEX, which are typically products of primary devolatilization reactions. When the steam-carbon-to-carbon ratio is increased to 1.5, a strong reduction in total tar content is observed. This indicates that additional steam promotes cracking and reforming reactions of tar precursors and intermediate compounds. At a steam-carbon ratio of 2, the minimum tar production is achieved. Heavy tar compounds are significantly reduced, confirming that higher steam availability enhanced secondary tar conversion reactions. In this slide, the effect of feedstock on process performance is shown. Serious sludge shows the highest hydrogen concentration among the tested feedstocks, but this behavior must be interpreted considering its very low fixed carbon content, around 3.1% in weight, as we have seen previously. Due to the limited amount of fixed carbon, gas-solid reactions such as char gasification are very weak, which explains the low CO concentration observed in the product gas. As a consequence, gas production from sewage sludge is largely dominated by the volatilization reaction, leading to high methane and light hydrocarbon contents. At 650 degrees C, reforming reactions are kinetically limited, but not negligible. Even a partial reforming of hydrocarbons can generate significant amounts of hydrogen, since reforming reactions produce a large amount of hydrogen per mole reacted. This explains why sewage sludge presents a high hydrogen molar fraction despite limited char gasification, together with high hydrocarbon concentrations and low carbon monoxide levels. When comparing lignocellulosic biomasses, clear differences in gas composition can be observed, even under identical operating conditions. Structural shows the highest hydrogen concentration among the lignocellulosic feedstock, together with the lowest methane and light hydrocarbon contents. In addition, structural also presents lower CO concentration compared to olive stone and grape seeds. This behavior can be explained by differences in intrinsic feedstock properties. Proximate and ultimate analysis show that structural has a higher ash content than the other lignocellulosic biomasses. These ash components may exert a mild catalytic effect, favoring secondary reforming reactions of methane, like hydrocarbons and tar precursors, even at the lowest temperature of 650 degrees C. As reforming reactions typically produce proportionally more hydrogen than carbon monoxide, enhanced reforming activity leads to a faster increase in hydrogen concentration, while carbon monoxide decreases in relative terms. This explains why structural produces a cleaner gas composition with higher hydrogen and lower hydrocarbon levels compared to olive stone and grape seeds. Now focusing on gas yield and fixed carbon conversion, a different perspective of the feedstock effect can be observed. CO2 sludge clearly shows the highest total gas yield among all feedstocks. However, this high gas yield is not related to fixed carbon conversion, since CO2 sludge contains a very low amount of fixed carbon. As discussed previously, gas production from CO2 sludge is largely dominated by the volatilization processes rather than char gasification. The limited contribution of gas-solid reactions explains that the observed gas yield cannot be attributed to the fixed carbon conversion. In contrast, CO2 sludge generates a very large amount of tar during the volatilization. Even though tar reforming is kinetically limited at 650, partial reforming of this large tar fraction still occurs. As reforming reactions generate a high number of gas moles, particularly hydrogen, the partial reforming of tar significantly increases the total gas volume produced. This explains both the high total gas yield and the high individual hydrogen yield observed for CO2 sludge. When comparing lignocellulosic biomasses, a different behavior is observed. Structure reaches the highest fixed carbon conversion among lignocellulosic feedstocks, leading to a higher total gas yield compared to olive stone and grape seeds. This behavior reflects the higher reactivity of structural. As a consequence of the higher carbon conversion, structural also shows the highest individual hydrogen yield among lignocellulosic biomasses. These results confirm that high gas yield can originate from very different pathways: the volatilization and tar reforming in CO2 sludge, or effective fixed carbon conversion in lignocellulosic biomasses such as structural. Finally, we analyze the effect of the feedstock on tar formation under identical gasification conditions. CO2 sludge clearly presents the highest collectible tar content among all feedstocks. As shown in the tar speciation, this tar is mainly dominated by BTEX compounds. This behavior is consistent with the volatilization-dominated nature of CO2 sludge gasification. When focusing on lignocellulosic biomasses, a different tar composition is observed. These feedstocks show a higher contribution of phenolic compounds, which are typically associated with lignin decomposition, among others. Among lignocellulosic biomasses, structural presents the lowest tar content, both in terms of gravimetric and collectible tar. This result is fully consistent with the cleaner gas composition and higher performance and higher reforming activity previously discussed. In contrast, grape seeds exhibit particularly high tar production. This indicates limited tar conversion in line with their lower gasification reactivity and reduced fixed carbon conversion observed in previous slides. Regarding sulfur compounds, clear differences are observed depending on the feedstock. CO2 sludge shows a significantly higher sulfur release compared to lignocellulosic biomasses. This behavior is directly related to its much higher sulfur content, as evidenced by the elemental analysis. In these cases, hydrogen sulfide is the dominant sulfur species detected in the system, while other sulfur-containing compounds such as COS, carbon sulfide, and methyl mercaptan are present only in minor amounts. The higher sulfur concentration observed for CO2 sludge is therefore mainly controlled by its intrinsic chemical composition rather than biopolitic conditions. This result highlights the importance of feedstock selection when considering downstream gas cleaning requirements and sulfur management. Finally, to conclude gasification, we can say that gasification is a flexible platform for converting biomass and biogenic waste into syngas, which can then be used for hydrogen fuel hydrogen, fuels, or chemicals. The key point is that syngas quality depends strongly on both operating conditions and feedstock properties. Temperature, steam to carbon ratio, equivalence ratio, bed material, ash composition, and reactor hydrodynamics all influence gas composition, tar formation, carbon conversion, and contaminant release. From the experimental results, temperature was one of the most important variables, increasing the temperature from 650 to 850 degrees Celsius. Because it was observed a clear increase in gas yield from 0.66 to 1.56 normal cubic meters per kilogram of biomass, and fixed carbon conversion from about 74 to 97%. At the same time, tar formation was strongly reduced, especially gravimetric tar, which decreased from 35.2 to 2.4 grams per normal cubic meter. Steam addition also promoted reforming and tar conversion, although at 650 degrees Celsius, the water-gas shift reaction was kinetically limited. As a result, hydrogen concentration did not increase linearly with steam to carbon ratio. Finally, the feedstock had a clear effect on gas quality, structure, and showed the cleanest behavior among the lignocellulosic materials, whereas serious sludge produce high hydrogen concentration, but also much higher tar and sulfur release. Overall, these results confirm that in biomass to hydrogen routes, such as HYIELD Project, gasification and syngas cleaning must be designed together in order to protect downstream hydrogen purification units. That's all, and thank you very much for your attention.
Okay, thank you very much, Ramon, for your presentation. I was checking the Q&A, but I don't see any questions. I don't know if anyone has any that they would like to do now. Okay, I guess not. In any case, if you come up with a question later on, just please feel free to reach out to us, and we will be glad to answer it. Thank you. I left a comment saying that the recording and the presentations will be available in a few days. We will most likely make a post, so you'll know they will be available in our website. Like I said, if there are no questions, then I guess we can wrap things up. So before we close, I would like to thank Andres and Ramon for their excellent presentations and for this overview of the gasification in general, but also for the HYIELD project. I would also like to thank all of you who have joined today. And like I said, if you have any questions, please reach out to us. And like I mentioned already, the recording and the presentations will be made available later on our website. So, okay, hold on. There is a question. What is about studies about olive cake orujillo? I guess that's for you, Ramon.
Yes, well, in fact, we only work with olive stone. But I think that they are quite different because in the case of olive stone, there are no rests of, for example, oil. But in the other residues coming from the oil mill, maybe there are some rest of oil, and that may affect clearly to the gasification process. But anyway, we never tested this material, although we wouldn't mind to do it, to be honest. Okay. If we are able to feed it into the reactor, that sometimes it is really very challenging to feed the material inside the gasifier. Okay.
Okay. Okay, so he asks again, but oil in olive cake are less than 3%.
Yeah, but maybe 3% it seems very low from a quantitative perspective. But once you are working at very high temperature in the gasifier, it may be important, especially, for example, in the kind of tars that you are going to produce, or even condensates, and all this stuff. Okay, so everything has to be studied before. Yeah.
Okay, another question then.
Yeah.
What?
Because I was trying to.
Okay. What are the feed conditions in the gasifier for the sludge?
The sludge was dried, and it was with a particle size of some millimeters. I think it was around, well, something comprised between 4 to 10 millimeters roughly. Okay. But it was always dry.
Okay. Is it clear, Alejandra, or do you have any follow-up questions? Okay, so if there is nothing else, then all right. So let's wrap things up. Like I said, if you have any questions, reach out. And like I said, the recording and the presentations will be made available in our website. Oh, yes. Okay. All right. We more questions. How much humidity?
Yeah, the humidity was, I think, comprised between 10 to 15%.
Okay.
There was another question, I think.
Okay, Alejandra is done. Then we have another question. Did you conduct the simulation in Aspen?
Well, this work was done by Sintef. That was done by Filippo.